Hello, in the previous clip we refreshed our memory about root locus and how one would be able to draw the root locus if you are given the open loop transfer function of a system. In this clip we shall take a look at how we can employ the tool of root locus to perform control system design. In order to do this, let us do it through a numerical example. So what we shall do is consider the plant P of S to be equal to 1 by S plus 1 times S plus 2 times S plus 3. So this is a third order plant. The root locus of this plant has been sketched by using MATLAB software, and the root locus is shown in this slide here. One of the most obvious applications of root locus is to be able to choose a proportional controller's gain such that a pair of poles of the closed loop system would be located where we want it to be located. So for instance, the root locus of the plant here tells us all the possible locations of the closed loop poles that has this plant P cascaded with a simple proportional controller as part of the open loop system. So in other words, I am drawing here a gain K that is cascaded with P of S, where P of S is given by this transfer function here, and a feedback loop that is wrapped around this combination essentially will have this root locus. Now suppose we want the dominant poles of this closed loop system to be located at some particular position. We know that it is going to be located on one or another of these branches of the root locus. Suppose we want the closed loop pole to be located at one particular point on the root locus, then we can use the root locus to determine the gain K that places the closed loop pole at that particular location. For instance, if let us say we want a pair of dominant closed loop poles, let me call them P1 and P1 bar, okay, to have a form P1 is equal to minus zeta omega n plus omega n square root of 1 minus zeta square, and P1 bar to be equal to minus zeta omega n minus omega n square root of 1 minus zeta square. If this is the form that I want my closed loop poles to have, then what we can do is employ root locus to find out the gain K that gives us, for example, a specified zeta. So if you notice this equation here, the term zeta is related to the angle that this pole makes with respect to the real axis. In fact, this angle that I have shown here will be given by pi minus cos inverse of zeta. So if I want my closed loop dominant closed loop poles to have a certain specified value of zeta, which in effect means that our closed loop system has a certain amount of damping, then what we can do is first we draw a straight line of slope dictated by the particular zeta that is given to us. So zeta equal to constant is a straight line that passes through the origin and is inclined with respect to the real axis by this angle pi minus cos inverse zeta. So the most simple application of root locus is to first draw that straight line and find where that straight line intersects the root locus, and that turns out to be this particular point here. Now we determine the gain of the controller K that will allow the closed loop pole to be located at this particular point, and that is the gain that our controller needs to have for our closed loop system to have a pair of dominant poles with that particular specified value of zeta. So this is one very simple application of root locus. A very similar application of root locus would be if you specify omega n. So you want your dominant closed loop poles to be of this form, P1 equal to minus zeta omega n plus minus omega n times square root of 1 minus zeta square, and you want it to have a certain frequency omega n. Now if omega n is specified to you, or in other words omega n is a constant, then what you would notice is that omega n equal to a constant represents a circle. So, the pole P1 and P1 bar would lie on a circle of radius given by omega n. That is because if I take the real part of P1, it is minus zeta omega n, the imaginary part of P1 is omega n square root of 1 minus zeta square, the real part of P1 plus the whole square plus the imaginary part of P1 the whole square, which is the square of the magnitude of this complex number, is essentially just going to be equal to omega n square. Therefore, if I specify omega n, it will move along the curve given by real part of P the square plus imaginary part of P the square is equal to omega n square. Real part of P essentially represents the x coordinate. So, this is going to be x square plus y square is equal to omega n square, and this equation essentially describes a circle of radius equal to omega n. So, the second straightforward application of root locus is to find out that gain k of the proportional controller that allows for the dominant poles of our system to have a specified frequency omega n. To do that, all we need to do is draw the circle of radius omega n and find out where it intersects the root locus of our plant. So, it so happens that in this case it is intersecting them at these two locations. Now, at these 2 points in the complex plane we determine the gain k, and once we have determined the gain k, then we know that our proportional controller needs to have the particular gain for our dominant poles P1 and P1 bar to have that particular omega n. So, designing a closed loop system using a proportional controller such that the closed loop system has a certain specified damping or a specified omega n for its dominant poles is one straightforward application of the notion of root locus. However, its scope is far bigger than what we have just discussed. Now, in this case you notice that we specified either omega n or zeta for our closed loop system. The problem is, if you want to specify both omega n and zeta, in other words both omega n and zeta are decided ahead of time, then you run into problems. So, we shall look at that in the next example. So, we come back to this plant P of s is equal to 1 by s plus 1 times s plus 2 times s plus 3, and we insist that its closed loop poles be located at PCL naught equal to minus 1.5 plus 2j and PCL naught bar equal to minus 1.5 minus 2j. So, you want to design a closed loop system for this particular plant that has its as its dominant poles minus 1.5 plus minus 2j. Now, in this graph, in this root locus, if I were to locate minus 1.5 plus minus 2j, I would notice that along the x axis I need to have minus 1.5, which is somewhere here, and minus 1.5 plus 2j would be this point here, that is PCL naught, and minus 1.5 minus 2j would be a point here. This is PCL naught complex conjugate. Now, we see that in this particular case it is impossible for a proportional controller to get us to have this particular closed loop dominant dynamics for our system, simply because by just using a proportional controller our closed loop poles can only lie on the root locus of our plant. So, if I were to change the gain k, the closed loop poles can vary along these particular curves. However, for this case the location where we want our closed loop pole to lie, the dominant closed loop pole to lie, is outside of the root locus. So, it is not possible to use a simple proportional controller as we did in the previous examples in order for us to realize this particular pair of dominant poles for our closed loop system. So, what should we do? The first thing that we need to do is to get the root locus of the overall open loop system, namely the controller times the plant, to pass through the point at which the closed loop pole has to lie. So, that is the first thing. The root locus has to pass through PCL naught and PCL naught bar. Of course, if it passes through PCL naught, it will automatically pass through PCL naught bar because the root locus is symmetric about the horizontal axis. So, that is the first thing that we need to do. So, we need to choose such a controller C of S that it allows the root locus to pass through the point PCL naught. Having chosen that controller, we have to then decide on the gain of the controller such that the closed loop pole is actually located exactly at PCL naught. So, the first step of choosing such a controller that the root locus passes through PCL naught will not automatically guarantee that the closed loop pole will be exactly at PCL naught. We have to now choose the gain of the controller appropriately to make sure that the closed loop dominant pole will be located at PCL naught and PCL naught bar. Of course, there will be one more pole on the other branch of the root locus, which we are not going to discuss because it is going to be to the left of these two poles and is therefore not going to be a dominant pole of our closed loop system. So, we have to therefore first get the root locus to pass through the point PCL naught. What does that mean? In practice, what that means is that the angle subtended by all the open loop poles and zeros of our system at the point PCL naught should be equal to minus pi or its cyclic equivalents. So, for at the moment we have a plant with 3 poles, namely pole at minus 1, minus 2 and minus 3. Let us compute the angle subtended by all these 3 poles put together at the point PCL naught. The angle subtended by the point minus 1 at PCL naught is given by this particular angle. I shall call it theta 1. The angle subtended by the pole minus 2 at PCL naught is given by this particular angle. I shall call it theta 2. The angle subtended by the third pole of the plant at minus 3 at the point PCL naught is given by this angle and I shall call that theta 3. So, the net angle of P of S at the point S is equal to PCL naught will be equal to minus of theta 1 minus theta 2 minus theta 3. The reason we have these negative signs in front of these angles is because they represent the angle subtended by the poles of our system, and poles are terms that appear in the denominator of this transfer function, and therefore the angles of these complex numbers s plus 1, this complex number is s plus 1 and the angle of 1 by s plus 1 is minus of theta 1, the angle of 1 by s plus 2 is minus of theta 2 and the angle of 1 by s plus 3 is minus of theta 3. Hence we have these negative signs here. Now, if we compute these angles from by using trigonometry, we know PCL naught, it is equal to minus 1.5 plus 2j, and we know the locations of these poles. So, it is quite straightforward for us to compute these angles. If we compute them, we get the sum of these angles to be equal to minus 233 degrees. Now, for the point PCL naught to be a point on the root locus, the angle has to actually be minus 180 degrees or its cyclic equivalents. Therefore, what you see is that there is a deficit of minus 53 degrees, which is essentially equal to minus 233 degrees plus 180 degrees. That needs to be compensated. So, I need to add plus 53 degrees to this phase in order for the net phase of our open loop system at this point PCL naught to be equal to minus 180 degrees. So, if I were to add plus 53 degrees here somehow, then I would have minus 233 plus 53 to be equal to minus 180 degrees, and I would be able to get the root locus to pass through the point PCL naught. Now, we need to choose a controller that provides to us a phase lead of plus 53 degrees at the point PCL naught. So, in other words, the angle of C, whichever controller that it is that we choose at the point S is equal to PCL naught should be equal to plus 53 degrees. Now, the question is, what controller do we pick? Here again we have a infinite number of controller structures that we can choose, all of which can potentially give us 53 degrees phase at the point PCL naught. By choosing different combinations of poles and zeros and appropriately locating the poles and zeros of the closed loops of the controller, we can get the net phase contributed by this combination of poles and zeros to be equal to 53 degrees, and there are infinitely many controller structures that will give us that same angle. So, how do we pick a suitable controller from among these infinitely many controllers? Once again, as we did in the case of Bode plots, we use simplicity as our guide for picking a suitable controller structure. We notice that we have to get positive angle of 53 degrees to be subtended at the point PCL naught. So, the simplest controller structure that allows us to do that is a simple 0. So, if I choose the controller C to be of the form S plus Z, then let us say I locate the point Z in the complex plane, let us say this is that point Z, okay. Then I choose this point Z in such a manner that the angle subtended by this point Z at the point PCL naught, which is given by this particular angle here, which I am shading here for the sake of clarity, that angle should be equal to plus 53 degrees. Now, I know what PCL naught is. So, PCL naught is minus 1.5 plus minus 2j. So, the height, its height from the real axis is essentially 2 units. So, I can use once again trigonometry to determine, and I know that this angle, the shaded angle has to be plus 53 degrees. So, I can determine therefore the location of Z from trigonometry, and I get that location to essentially be equal to Z 3 units. So, Z should be placed at S is equal to minus 3. This is all well and good, but there is one simple problem with this control structure, namely that it is not a causal controller. So, we have a transfer function here which has no denominator polynomial at all and just a numerator polynomial. So, it cannot be physically realized. If you recollect, we need to have physical controllers or physical plants to be strictly proper transfer functions or at best proper transfer functions, or in other words, the degree of the numerator polynomial should be either less than or equal to the degree of the denominator polynomial. It cannot be greater than the degree of the denominator polynomial. Therefore, for the sake of causality, what we have to do is we have to also choose to have a pole for the plant. So, our controller structure, interim structure would look something like this. We are not done with the design yet. So, this is not our final controller, but if we choose a controller of this structure, then if we place the 0 Z at S is equal to minus 3, then we would get plus 53 degrees at the point PCL naught from that 0, and that will cause the net angle subtended by the controller times the plant at that particular point to be equal to minus 180 degrees. However, because we have introduced this pole, the pole will also contribute to a small phase, negative phase. Now, if we choose to place the pole at a fairly distant location, so in this particular case I have chosen to place the pole at P equal to 11. So, or in other words, S is equal to minus 11, that is the place where I have chosen to place the pole. Now, if we place the pole at that location, we can, so that point would be somewhere outside of this graph. Then we can compute the angle subtended by that pole at the location PCL naught. So, we can compute the angle of 1 by S plus P at the point PCL naught, and if we do that, we find that that angle is equal to 12 degrees with a minus sign, because this is a pole. So, essentially therefore, we have an extra negative angle that has been added on to the already existing negative angle of minus 233 degrees by this extra controller pole that we had to incorporate, and this controller pole had to be incorporated in the interest of causality of the controller's transfer function. Now, our zero's position has to be fine tuned a little bit, because it has to now also compensate for this extra negative angle that has been supplied by this, by the controller pole. So, now instead of having to compensate for minus 53 degrees difference between the angle at the point PCL naught and the angle necessary for PCL naught to be a point on the root locus, namely minus 180 degrees. One has to have a controller whose 0 subtends an angle of not plus 53 degrees, but instead plus 53 plus 12 degrees. So, this plus 12 degrees is to compensate for the extra negative phase that has been contributed by the term S plus P, or in other words the 0 has to subtend an angle of plus 65 degrees at the point PCL naught. At S angle of S plus Z at the point S is equal to PCL naught has to be equal to plus 65 degrees. Now, if one once again employs trigonometry to compute the location Z at which the angle subtended by that 0 at the point PCL naught, in other words the angle of the shaded angle in this figure here, which I am once again indicating by means of this arrow here. For that angle to be equal to plus 65 degrees, one can compute that the 0 has to be placed at S is equal to minus 2.44, or in other words the term Z in this particular controller would be equal to 2.44. The new value of Z has to be equal to 2.44. Now, when we have the 0 at S is equal to minus 2.44 and a pole at S is equal to minus 11, notice that the pole location was rather arbitrary. We chose it to be at minus 11, we could have chosen it to be at other locations also. In practice we choose it on the basis of available bandwidth for implementation of our overall control system. So, in this case we are only discussing the theory of control design, so we shall not look at the practical aspects. So, here we have chosen to place it arbitrarily. This controller structure allows the root locus to pass through the point PCL naught and PCL naught bar. So, now there is hope for us to place our closed loop pole at PCL naught and PCL naught bar by choosing an appropriate gain K for our controller C of S. Now, how do we determine the gain K? What we need to do is to apply the condition for root locus. So, if a point PCL naught is a point on the root locus, then 1 plus K times C times P, where C is the controller transfer function, P is the plant transfer function, evaluated at the point S is equal to PCL naught should be equal to 0. This by definition is valid for all points on the root locus, and therefore is also going to be valid for point PCL naught, because it is now a point on the root locus. So, to determine the controller gain K, therefore all we need to do is to compute K as K being equal to minus 1 by C times P, where C is given by this particular transfer function S plus Z by S plus P, where Z is 2.44 and P is 11, and the plant transfer function of course has already been specified to us and I am underlining it there for you. So, if we use this equation and compute the gain K, we find that we get it to be equal to 46.67. Therefore, the controller that allows our dominant closed loop poles to lie at minus 1.5 plus minus 2j is given by C of S is equal to 46.67 times S plus 2.44 divided by S plus 11, and this completes our design. Note that our closed loop poles will not be located only at these two locations. You have another branch of the root locus also on this side, and therefore you will have a closed loop pole also lying on that branch. But since that pole is much farther away from the origin compared to PCL naught and PCL naught bar, it will not dominate the dynamics of the overall closed loop system, and therefore we do not need to worry about its exact position. So, what I have done here is to show you the root locus of the system that employs this particular controller, the one that we designed in the previous slide, along with this plant. And what you see therefore is that we have the root locus passing through the 2 points minus 1.5 plus minus 2j, and for this particular gain it is going to be the closed loop pole is actually going to be located exactly at minus 1.5 plus minus 2j. So, we would have one more pole on the on this branch of the root locus between this pole and that 0, and another pole on the other branch of the root locus, that is somewhere here. So since these poles are not as close to the origin as the two poles minus 1.5 plus minus 2j, they will not dominate the response of the closed loop system. Now, having seen how we can employ root locus in order to get a certain pair of points in the complex plane to be the dominant pole locations, even when those points do not on their own lie on the root locus of the plant, we shall now take another example to further explore this particular aspect of root locus based design. So, we shall come back to this same plant, P of s is equal to 1 by s plus 1 times s plus 2 times s plus 3, and this time earlier in the previous example we wanted the closed loop poles to be at minus 1.5 plus minus 2j. Here we shall expect the closed loop pole PCL naught to be at minus 3 plus 3j and its complex conjugate PCL naught bar to be minus 3 minus 3j. So, in this complex plane, if I were to represent minus 3 plus 3j, it would be somewhere here. So, this would be PCL naught and this would be its complex conjugate would be PCL naught bar. So, we want the closed loop pole to be located at PCL naught, the dominant closed loop poles to be located at PCL naught and PCL naught bar. How do we design a controller that gets this to happen? If you look at this problem, it does not look substantially different from the problem that we considered in the previous example. Once again, this is a case where the points PCL naught and PCL naught bar are not lying on the root locus of the plant. So, what we have to do is to adopt essentially a two-step based approach. In the first step, we choose such a controller that it gets the root locus of the open loop system, namely the controller times the plant, to pass through the point PCL naught, and the second step is to choose the controller gain k such that the closed loop pole actually lies at the point PCL naught and PCL naught bar. So, these are the two steps that we have to adopt, and that is what we would have to do even here. But there is a small catch in this particular problem, and hence I am separately discussing it. So, if you compute once again the angle subtended by the open loop poles, the three open loop poles of the plant, namely at minus 3 and minus 2 and minus 1 at the point PCL naught. So, once again we can do that from trigonometry. So, this is the angle theta 1 that is subtended by the complex number s plus 1 at the point PCL naught, and this is theta 2 and this is theta 3. We would have the angle of P of s at the point s is equal to PCL naught to be equal to minus of theta 1 minus of theta 2 minus of theta 3. And if one uses trigonometry and computes these angles, then we find that the net angle is going to be equal to minus 322 degrees. Now, for this point PCL naught to be a point on the root locus of the open loop system, we need the angle of course to be equal to minus 180 degrees. So, there is a difference, a very large difference of minus 142 degrees between what the net angle at the point PCL naught has to be and what it actually is. Now, if we were to choose to go with a single 0 for our controller in order to supply this positive angle of 142 degrees, then that 0 would probably have to be located on the right half of the complex plane. So, our 0 might have to be located here somewhere on the right half of the complex plane for the angle subtended by that 0 at the point PCL naught to be equal to plus 142 degrees. And the problem with locating a 0 on the right half of the complex plane is that it becomes a non-minimum phase 0, and it is something that we wish to avoid for reasons that we will get to in other lectures, in later lectures. So, for the moment let us assume that it is not wise and desirable to have a 0 on the right half of the complex plane. So, let us not choose to place a single 0 there. So, we have to find other ways by which we can compensate for this difference of 142 degrees between what we desire as a net angle and what we have. One way to do it is to go with 2 zeros. So, if we have a controller C of S to be equal to S plus Z1 times S plus Z2 as the starting initial structure for the controller. Of course, this is not a causal controller, but for the moment let us assume that we use the 2 zeros to get the angle of 142 degrees at the point PCL naught. Then we have to pick Z1 and Z2 such that the angle of S plus Z1 plus the angle of S plus Z2 at the point S is equal to PCL naught is equal to plus 142 degrees. Now, we have freedom in locating Z1 and Z2 wherever we want. If we pick Z1, then we need to choose Z2 such that the angles subtended by the two together add up to 142 degrees. So, what we can do is we can choose to place Z1 exactly at S is equal to minus 3. So, at this location here I am shading it there. So, in other words, this controller 0 Z1 essentially cancels the plant pole at S is equal to minus 3. Now, if you notice, this 0 subtends an angle of plus theta 3 at the point PCL naught, and a simple observation will reveal that theta 3 is equal to 90 degrees, and therefore, the angle S plus Z1 at the point PCL naught will be equal to 90 degrees if I choose Z1 to be equal to 3. So, what that means is that my angle S plus Z2 has to be such that the sum should add up to 142 degrees, and that will reveal that my angle S plus Z2 has to be equal to 52 degrees. So, now that I know what angle Z2 has to subtend at the point PCL naught, I can use trigonometry to locate Z2 at some suitable location to the left of the point Z1 such that it subtends an angle of, so I can choose to locate it here and use trigonometry to determine its exact position, so that this angle is going to be equal to plus 52 degrees. However, exactly as with the previous controller, we have a non-causal implementation with just the 2 zeros being the ones that are supplying the phase necessary to make the point PCL naught a point on the root locus. Therefore, we have to also choose to have 2 poles for this controller, so that it becomes a causal controller whose denominator polynomial is at least of the same degree as the numerator polynomial. In this case again, we have freedom in placing these poles wherever we want, and I shall choose to place them at the same position. So, I shall choose the denominator to be of the form S plus P the whole square, and I shall choose also to locate the point P at 30, or in other words, the pole of the controller is at S is equal to minus 30. Now, once again, this point S is equal to minus 30 where I have chosen to locate my controller pole is rather arbitrary. In practice, this location has to be decided on the basis of the available bandwidth for the controller, but in general we chose it to be sufficiently far away in the hope that that far away pole will not contribute to a very large negative angle at the point PCL naught. So, the farther away it is, the smaller is its angular contribution at the point PCL naught, and in this case I have assumed that S is equal to minus 30 is adequately far away for our particular purpose. So, if we were to compute the phase contributed by a single pole, in other words, if I were to calculate 1 by S plus P at the point PCL naught, S is equal to PCL naught, I would get that to be equal to minus 6.5 degrees. So, the 2 poles put together therefore contribute to minus 6.5, angle of 1 by S plus P the whole square therefore at the point S is equal to PCL naught will be equal to minus 13 degrees. So, what we now have to do is to fine tune the positions of Z1 and Z2 so that they now compensate for this extra phase deficit that has come about because of the 2 poles that we have added to the controller in the interest of causality. So, earlier the 2 were subtending angles 90 degrees and 52 degrees respectively at the point PCL naught. Now, they have to subtend 90 plus 52 plus 13 degrees. Now we can fine tune both the positions or only one of the positions of the 0. In this case I shall choose not to move the 0 z1, I shall choose to continue to locate it at z1 is equal to 3. I shall choose the location of z2 in such a manner that the net phase of z2 is now going to be not 52 degrees, but instead 52 plus 13 degrees. So the angle of S plus z2 at the point S is equal to PCL naught has been chosen to be equal to 52 plus 13 degrees, which is going to be equal to 65 degrees. If I choose this to be the angle of S plus z2, then the angle of S plus z2 plus S plus z1 is going to be equal to 142 plus 13 degrees, which is 155 degrees, and with that I will be able to get the net angle at the point PCL naught to be equal to minus 180 degrees. So from trigonometry I can find out that location z2 at which this angle is going to be equal to 65 degrees, and I find that to be equal to 4.44. So z2 has to be at equal to 4.44, or the 0 has to be placed at S is equal to minus 4.44 for the angle subtended by that 0 at the point PCL naught to be equal to 65 degrees. So our tentative controller therefore is going to be of the form S plus 3 times S plus 4.44 divided by S plus 30 the whole square. Now this controller, when cascaded with this plant, will cause the root locus to pass through the points PCL naught and PCL naught bar, but this controller as it exists will not guarantee that the closed loop pole will lie exactly at PCL naught and PCL naught bar. It may be somewhere else on the root locus. What has to be done in order to get it to be exactly at PCL naught and PCL naught bar is to choose an appropriate gain k for the controller in order to get the closed loop poles to be located at these two particular locations. To find the value of the gain k, we employ the standard equation for root locus, namely 1 plus k times Cp at the point S is equal to PCL naught to be equal to 0, or in other words the gain k necessary would be equal to minus 1 by C of S times P of S at the point S is equal to PCL naught. So if we use this equation to compute the gain k, I would get the gain to be equal to 2542. Therefore our controller C of S is going to be given by C equal to 2542 times S plus 3 times S plus 4.44 divided by S plus 30 the whole square. Now this controller not only ensures that the root locus passes through PCL naught, but actually makes sure that the closed loop poles would be located, one pair of closed loop poles would be located at PCL naught and PCL naught bar. There will be other closed loop poles on other branches of the root locus. So in the next slide I have plotted the root locus for the overall system, namely this particular controller C of S and this particular plant P of S with the gain 2542 as the controller gain, and you notice that the closed loop poles would be located exactly where we want them to be situated. The other closed loop pole would be located on this particular branch of the root locus, and since it is significantly to the left of these two poles, that pole will not be a dominant pole of the closed loop system, and hence will not significantly affect the dynamics of the closed loop system. Thus far we have seen how root locus can be used as a tool to design for stability of the closed loop system, or in other words to get the dominant poles of the closed loop system to be exactly where we want them to be. If we move the dominant pole significantly to the left of the imaginary axis, we are improving the stability of the closed loop system, or if it is slightly to the right, then, or if it is closer to the imaginary axis, we are essentially resulting in a closed loop system with slightly reduced damping. But we cannot focus only on the stability considerations. As control engineers we also have to look at the performance considerations. How do we engineer control systems to have a desired amount of rejection of disturbances, may it be input disturbance or output disturbance, or how can we get it to track references with a desired level of accuracy. That is not very easy to do in root locus, because unlike in Bode plots we cannot specify in a very transparent manner the performance specifications and the necessary gain that the controller needs to have in order for it to meet those particular performance requirements. Nevertheless, for simple cases it is possible to use root locus to also satisfy performance requirements. For instance, if you want the same plant P of S to have 0 steady state error to constant inputs, or in other words DC inputs, then you note that in order for any system, control system, to have 0 steady state error to DC references or steady references, then we need to have an integrator as part of our open loop control structure. That is because an integrator results in infinite loop gain at omega equal to 0, which essentially corresponds to steady inputs, and thereby enables achieving 0 steady state error to tracking to DC references. However, if we were to introduce a simple integrator, as I have done in this particular example, what you notice is that the root locus will change dramatically. In fact, this is one of the drawbacks of root locus as a tool. In the case of Bode plots, when we had the Bode plot of a plant and a controller, then the Bode plot of the overall open loop system was simply the summation of the Bode plots of the plant and the controller. So, if I had the Bode plot of the controller and I modified the Bode plot of the controller a little bit, I can easily anticipate how the overall Bode plot would change. In the case of root locus, however, such a superposition or summation property is not valid. So, the Bode plot of a new controller times a existing open loop system can be extremely different from the Bode plot of the original open loop system itself, and that is precisely what has been shown in this graph here. So, the red dotted curve here shows the root locus for the plant P of S, and the blue curves here show the root locus for the open loop system P of S times C of S, where C of S is given by an integral controller. So, what you see is that the blue curve is substantially different than when compared to the red dashed curve, and therefore, if we had taken the trouble to design the dominant dynamics of our closed loop system, or in other words we had already placed the dominant closed loop poles at PCL naught and PCL naught bar, inclusion of this integrator term will completely spoil the design, because the root locus will now no longer pass through that original point PCL naught and PCL naught bar, and therefore we will not be able to realize those particular dominant dynamics. So, how do we address this issue? In our attempt to ensure good performance in terms of tracking DC references well, we have now spoiled our dominant dynamics design. In order to address this issue, what we can do is, instead of adding a single pole at the origin as what we would do if we use a simple integrator as the controller, let us say we add a pole 0 pair. So, in addition to this pole at the origin, let us say I also add a 0 very close to the origin. So, when I say very close to the origin, I mean that I am adding the 0 at a distance that is much smaller than the distances of the other plant's poles and zeros from the origin. Now, what happens is that because this pole and 0 pair are very close to one another, or in other words I am having a controller of the form C of S is equal to S plus alpha divided by S. That is the kind of controller structure that I have picked, where alpha is very close to 0. Now, because alpha is very close to 0, if I were to pick a point on the root locus of the original plant, or in other words, or the root locus of the open loop system before introduction of this integrator term, what we notice is that for a point on that root locus, the angle subtended by the 0 and the angle subtended by the integrator are very close to one another, and because they are very close to one another and the angle subtended by the 0 is going to be the negative of the angle subtended by the pole, namely the integrator, the algebraic sum of these two angles will essentially go to 0 or will be very close to 0. What this essentially means therefore is that if we choose a pole 0 pair that is very close to the origin, then that pole 0 pair will not affect the overall phase of points on an already existing root locus. So, if already we are getting the net phase of our open loop system at some point PCL naught to be equal to minus 180 degrees, the phase because of these two, this combination of pole and 0 will not be very different from minus 180 degrees. It may be a little bit larger or a little bit smaller depending on the exact positions of these two terms. And what that in turn would mean is that the root locus of the new system that incorporates the 0 and this pole will be very nearly the same as the root locus of the original system itself. There will be a small deviation depending on how far away we have placed this 0 from the integrator, but it will not be substantial enough for us to be concerned that our dominant dynamics design would have been spoiled. And that is precisely what has been done in this example that I have considered. Here we have chosen to place a pole at s is equal to 0.01, and this was intended to improve the performance in the low frequency region. And in order to prevent the pole added at s is equal to minus 0.01 from affecting the overall root locus, we have chosen to also add a 0 close by at s is equal to 0.1. So, the two together will result in an amplification in gain of by a factor of 10 for frequencies below omega equal to 0.01 radian per second. As far as the root locus is concerned, what I have plotted here is the root locus of the original plant in the dashed curve and the root locus of the plant times this controller in the blue curve. And what you see is that these two curves are very close to one another, which indicates that this particular controller allows us to improve low frequency performance by adding a gain of 10 in the low frequency region, but without changing the without significantly changing the dominant dynamics that we might have already designed for this particular system. And if one notices, this controller structure is essentially that of a lag compensator. So, having talked about how one would go about doing design using root locus, a couple of comparisons between root locus and Bode plots are in order. So, the first is the utility of one with respect to the other. As we discussed in the previous clip, the main purpose of control engineers is to contend with uncertainties either in the plant or in its environment, or in other words, we have to ensure robustness of the system to variation in plant parameters and prevent disturbances occurring either at the input or at the output from affecting the overall response of the system. With this as the primary objective of control engineering, we notice that our performance specifications are more important. We have to satisfy our performance specification. We have to reject disturbances by the specified amount, we have to track references with a desired degree of accuracy. That is really what we get paid for. But in our effort to do that, we might end up destabilizing our closed loop system, and hence the importance of Nyquist stability theory and phase margin and gain margin and so on in performing control design. Therefore, performance specifications are more important, meeting performance specifications are more important than designing a closed loop system with the desired dominant poles or the desired dominant dynamics. As we saw in this particular clip, representing the constraints on the overall open loop system that would arise due to the performance specifications in terms of disturbance rejection or reference tracking is difficult in case of root locus, whereas one can readily represent in a Bode plot the necessary loop gain or the necessary controller gain for us to be able to track references or reject disturbances in certain frequency ranges. And hence root locus is not as powerful a tool as Bode plots when we are performing control design, but still it is a very useful complementary tool to analyze the overall response of control systems once we are done with the design of a controller. So, although one might not always want to use root locus as the tool of choice for performing control design, owing to the difficulties associated with satisfying performance specifications, even though stability specifications are very easy to satisfy because we know exactly where the closed loop poles are going to be located, the root locus still performs a very valuable service by allowing us to check where the closed loop poles, where all the closed loop poles of our system are. Now, this brings us to a problem that we encountered when we were doing Bode plot based design. So, to refresh your memory, we had designed a proportional integral controller C of s is equal to s plus 1 by s for the plant P of s, which was nominally given by P of s was equal to 10 by s by 10 plus 1 times s by 50 plus 1 times s by 300 plus 1. So, this was the plant that we had considered in the clip where we had performed control design using Bode plots, and the PI controller was chosen in order for us to improve the mid frequency performance. When we plotted the step response of the closed loop system, we noticed that there was a long inexplicable tail in the response of the closed loop system that could not be explained by using Bode plots. There was nothing in the Bode plot of the open loop system that could hint at the possibility of such a tail existing in the response of the closed loop system. However, since root locus allows us to locate all the closed loop poles, in principle we should be able to answer this question by using root locus. How do we explain the existence of this pole? So, if this is the controller of that we are using and this is the plant transfer function, then the overall transmission function whose step response we are plotting here is given by T of s is equal to C times P divided by 1 plus C times P, and if one were to simplify this, one would get this to be equal to s plus 1 divided by s by 10 plus 1 times s by 50 plus 1 times s by 500 plus 1. So, these are all the plant poles times s, which is the controller pole, plus s plus 1. So, this is the denominator polynomial of our system. Now, just inspection of this will not reveal to us how we are getting this long tail. To understand this, let us plot the root locus for the transfer function 1 plus k times s plus 1 divided by s times s by 10 plus 1 times s by 50 plus 1 times s by 300 plus 1. Anyway, it is the zeros of this particular transfer function that are going to be the poles of our closed loop system, and that is what is going to dictate the step response of our closed loop system. So, if one were to plot the root locus for this particular denominator transfer function, then one would notice that we have a pole at the origin at s is equal to 0, and then we have poles at s is equal to minus 10 and then minus 50 and a very far away pole at s is equal to minus 300, minus 10, minus 50 and minus 300, and then we have a 0 also at s is equal to minus 1. Now, as far as the root locus is concerned, we would have a branch of the root locus starting from this pole, the integrator, and ending in the 0. So, this is one branch. Then we would have one more branch starting at minus 10, a second branch starting at minus 50. These two branches will meet at a certain point and break away into the complex plane, and then you would have a third branch starting at minus 300 and then and going towards negative infinity, and the branches that broke away will eventually asymptotically approach straight lines that are inclined at plus minus 60 degrees to the real axis. So, this is how the root locus of the overall open loop system would appear. So, we would have one closed loop pole on this branch, we would have one closed loop pole on that branch, we would have one closed loop pole on that branch, and we would have one closed loop pole on this branch, on the branch near the origin, and it is that closed loop pole which is of interest to us, because if I were to represent T of S in terms of these closed loop poles, I would have T of S to be equal to S plus 1 divided by S plus alpha, where alpha is a point here in between the points minus 1 and 0, times, if I call this point P1 and call that point P1 bar, and if I were to call this point P2, then we would have S plus P1 times S plus P1 bar times S plus P2. This would be the structure of our closed loop transfer function. So let us focus on this term S plus 1 by S plus 1 by S plus alpha. We note that this term alpha is a very slow pole, because it is situated much closer to the origin compared to the other poles. P1, P1 bar, P2 are all on branches of the root locus that are quite far away from the origin compared to the point alpha, and it is this slow pole that is responsible for this long tail in the response of the closed loop system. But we do see that this long tail does not end up dominating the step response of the closed loop system. How does one explain that? One can easily understand that by noting that you have this term S plus 1 also in the numerator, and when the gain is high, the point alpha will be close to the point minus 1, because the root locus always ends in a 0. Therefore, when gain is high, when the open loop gain is high, the point alpha will be close to the point 1. So the numerator S plus 1 will essentially cancel this pole, and therefore will prevent it from dominating the response of the overall system. In this particular case, however, the gain of our controller C of S is simply equal to 1, which means that for this particular case our alpha was not really as close to the point S is equal to minus 1 as we wanted it to be, and as a consequence of that, the effect of this slow pole was not adequately suppressed by the 0 S plus 1, and the fact that it was not suppressed was what contributed to the existence of this long tail in the closed loop response of our system. So what you see in this example is a situation that one could not readily explain by using Bode plot for analysis, whereas one can easily explain with great clarity when one employs root locus as a tool for analysis. Thank you.